All right, so today we're doing something really cool. We're going to put Earth and its, seemingly quiet companion, the moon, head to head. And we're going to do it by listening to them, well, rumble and quake. I mean, it's a great question, isn't it? We can't exactly drill a hole to the center of the Earth, and forget about doing that on the moon. So, how in the world do we figure out what's going on thousands of kilometers right under our feet?
Well, the answer is actually pretty simple and kind of beautiful. You just listen. Yeah, you listen. Every single tremor, every little quake sends these waves vibrating through the planet's guts, and those waves carry a story about everything they pass through. Our job is just to learn how to read that story.
So, you probably think the moon is just this dead, silent rock in the sky, right? Well, think again. Get a load of this number. Between 1969 and 1977, the seismometers the Apollo astronauts left behind picked up this many separate seismic events. That's right, over 13,000 moonquakes. The silent moon? Yeah, not so silent after all.
Okay, so let's pop open the hood on our investigative toolkit here. We're going to be using a science called seismology to basically create a profile for our two celestial suspects.
The best way to think about it is like a planetary ultrasound. Seriously, a quake happens, boom, and it sends these seismic waves shooting out in all directions. By measuring how those waves travel, how they bend, how they bounce off things, how they speed up or slow down, we can build this incredibly detailed map of a planet's insides, all the way from the crust right down to the core.
All right, first up, our home turf, planet Earth. This is the one we know the best, so it's the perfect baseline for our comparison. Let's take a look at its seismic signature, its planetary heartbeat, if you will.
So our planet is basically built like an onion. We're living on the super thin, brittle outer skin. That's the crust. Right below that, you've got the mantle, which has this hot, kind of gooey, flowing upper part and a more solid lower part. And then, smack in the middle, you have a liquid outer core sloshing around a solid inner core. And here's the key. Each one of these layers totally changes how those seismic waves travel through it.
Okay, so take a look at this. This chart tells us exactly where the action is happening. See how many earthquakes there are compared to how deep they are? It's pretty obvious, right? Almost all the shaking, the vast majority of it, is happening way up here, in the shallow parts. The deeper you go, the quieter it gets. The number of quakes just plummets. And that, right there, is our first crucial clue. I want you to burn this into your brain. On Earth, the seismic action is a shallow game. It's all happening in the crust and the upper mantle. It pretty much never happens deeper than 700 kilometers. Got it? Okay, tuck that away. It's going to be important. Okay, now let's pivot and turn our attention to the moon. Remember, it's smaller, it's colder, and it doesn't have the plate tectonics that we have. So keeping that in mind, what in the world is causing all those thousands of moonquakes we mentioned earlier? The data from the Apollo missions gave us this absolutely fascinating breakdown. So, okay, you've got quakes from meteorites hitting the surface. Makes sense. Then you have these thermal quakes. That's just the crust expanding and contracting as it heats and cools. But then, look at this last category. This is the stunner. Over 7,400 deep moonquakes coming from way, way down in the lower mantle. This is the big mystery, the real head-scratcher. Remember that 700-kilometer limit on Earth? Well, on the moon, the most common type of quake only starts around there and goes even deeper. It's the complete opposite of what we see here at home. So what is going on? All right, it's time for the showdown. We're going to lay all the evidence out, side by side. We're comparing Earth and the moon, layer by layer, to finally crack this seismic puzzle. So let's start at the top, with the crust. On the surface, they look kind of similar, right? Both are solid rock, roughly the same thickness. But the reason they shake is completely different. Earth's crust is getting constantly crunched and stretched by our moving tectonic plates. The moon, though, its crust is mostly just getting rattled by things hitting it from the outside, like meteorites or the daily temperature swings. Okay, now we get to the really juicy part, the mantle. This is where everything changes. Earth's upper mantle is hot. It's dynamic. It's basically a layer of slowly churning rock. Think of a super thick pot of soup boiling. That churning is what moves our continents and causes all our shallow quakes. But the moon's mantle, it's cool, it's solid, it's rigid. And yet, unbelievably, this is where its deepest, most common quakes are coming from. And this slide just lays it all out, doesn't it? It perfectly sums up their different personalities. Earth is this hot, dynamic world. It has a churning engine just below the surface that's driving all the action. The moon, on the other hand, is cool and rigid. It's like an old, solid structure that's still settling, releasing ancient stress from deep inside. Okay, we've looked at all the clues, we've compared the suspects, so what's the final verdict? What is the story these two completely different seismic signatures are telling us about where these worlds came from and where they're going?
The seismic evidence really spells it all out for us. Earth's quakes are shallow because our planet is powered by that hot, churning engine right below the crust. It's the sign of a world that is very much alive and kicking. The moon's quakes, though, are super deep because it's a cooler, more solid body, just slowly releasing old stress from deep inside. So it's not really about one being active and the other being dead. It's about why they're active. One is driven by present-day heat, and the other, well, it's just settling into a long, cold sleep.
So in the end, when we listen to these quakes, we're not just hearing rocks break. We're hearing a story of evolution, a tale of two worlds on two very different paths. One is still hot and dynamic, and the other is slowly, gracefully cooling toward silence. And that makes you wonder, doesn't it? If we could come back and listen again in, say, 1 billion years, would Earth's loud, shallow heartbeat have finally faded to match the moon's deep, quiet whisper?